the little hub here in Missoula is just one of hundreds, if not thousands, around the world that are mining Bitcoin and maintaining the so-called blockchain ledger, and they have electricity issues. A lot of their electricity goes into running servers, of course. They got about 10,000 servers over there, but they also have a lot of inductive loads in the form of fans. So a lot of and that's what's making the most of the noise over there. So I have a new engineering firm here in town. There are five partners. I'm serving as the CEO. Patrick Brown's my chief operating officer. He's a biomass expert. I also have my chief marketing officer here in town, B.D. Erickson. We're going to show you some of his power conditioning equipment today. He's got 6,000 of these units around the world. In fact, he's got both a 60 hertz unit as well as a 50 hertz unit for international use. My chief science officer, Mike Holacek, is in Whitefish, Montana. He's a biochar expert, so he's done a lot of things, helping the forest products industry do things with their waste, basically taking that carbon and sequestering it into soil enhancement. And then my chief technical officer, Brian Jackson, is also a licensed professional engineer with a lot of experience in wind, big power purchase agreements, and also organic farming. So those are the five of us. But today we're just going to focus mainly on the power conditioning. As I said, we've got an opportunity here at the Project Spokane. We're also working with the hospital and a few other larger installations, but there are also some smaller residential devices that we sell to. So that's our company. This is our little tagline, sort of tagging on the end of this book of mine that's coming out. One of the things I'm interested in the building code is how do you reduce the waste streams that are coming out of them, or at least do a little better triage so that things aren't all just kind of ending up in the landfill. Okay. So I'm going to start off just doing a little bit of electrical power primer. For those of you who are interested, it's hard not to get on my academic soapbox. So I'll just go through a little bit of the math and some of the physics and some of the ideas, and then Patrick's going to actually give the demo here. So as I was mentioning out there at Project Spokane, the thing we're targeting mainly are the inductive loads. So this little curly Q represents a motor, and as you're probably aware, if you're ever taking the motor apart, you'll see meters, if not miles, of copper wound around, and that tends to cause some distortions in the sinusoidal AC wave that's coming at it. A pure load is a resistive load. That's typically a light bulb, something that's just making heat. A lot of the transistors that you see, if you put your hand on the back of your laptop, that fan is just blowing the heat away from shoving electrons back and forth through circuits. And what we do with our power conditioners is put in a capacitor that balances the inductive load. So bringing that sinusoid back to its pure form, which is the load that motors like to see. And I've just shown you various ways that you can connect either in series, in parallel, or some combination thereof. Our strategy is to put a capacitor in parallel with an inductive load to correct the so-called power factor, which I will explain shortly. Okay, so if you want to do a little more research on it, there's some neat animations out here at falstad.com. You can sort of play with the capacitance, the inductors. So if you're actually going to design one of these circuits, that's what you need to do. You actually need to go in there and work on that. What I'm plotting here on this axis is voltage and current. So in order to measure power, as I just mentioned, Project Spokane is running at 20 megawatts, and I think I can't remember the actual voltage coming in there, but it's on the order of kilovolts. You multiply kilovolts by hundreds of amps, and you're on the order of megawatts. So I plotted volts here in blue, and then over the top is current. That's sort of the ideal situation. That's what you would see in a purely resistive load. As soon as you start adding inductors, which is denoted by L, the current tends to lag behind the voltage. So there's a little bit of a delay there, and I'll show you some mechanical analogies. If you add a purely capacitive load, it tends to lead it. It's almost like pushing water through a garden hose. With pressure, it takes a while for all that current to get through the garden hose. That's the case of an inductor versus a bucket. If you're just pouring water into it, it'll take all the flow that you want very quickly. So that's the mechanical analogy. And I've tried to show that too. If you just had two buckets on a teeter-totter, the inductor tends to add to sloshing, whereas the buckets sort of capture the water in a mechanical analogy. This one's more my favorite though. If you've got a guy out plowing a field, this is the so-called power triangle. So at the bottom is what's called true power or real power, the resistance, which is what you're after. Same thing in a field. What you're really trying to do is get the field plowed, right? You're not out here for a joy buggy ride getting bounced around. So this is this sort of bouncing on the back that you're trying to avoid. The same reason you would put a suspension on your car. That's why you put on the dampers to bring that back down. When this triangle gets shorter and shorter, you get what's called a power factor of unity. So that's what we're sort of after by putting just enough capacitance or damping to take care of all the bouncing in the circuit that the motors are causing. And then just an example to show that these things work. I've done this at my house. So this is just hooking up a capacitor across a couple legs while I've got my washing machine on, for example, or anything that's got a motor in it. So this is time in seconds. So I guess I was running this right around noon. 2 minutes after, 2 minutes and 53, 2:04. So this is with the circuit off, and what you can see here is the phase angle. So with it off, I'm 14 degrees out of phase. So remember those two sine waves, if they're right on top of each other, the phase is 0. That's your ideal. And the more lag or lead you get, the higher that green line gets. Well, as soon as I turn it on, I come down and I'm closer to unity. I'm now at just 6 degrees off. And then the other one, you can see that the phase and the power factor are sort of inversely proportional. But prior to turning the device on, I was at a power factor of about 0.96. After I turned it on, I got up to 0.99. And that actually does result, believe it or not, in true power savings. You actually reduce the amount of amps that go through. You still have the same volts, of course, on the circuit. You're not going to change the line voltage, but you're reducing the amount of amperage that comes through to do the same amount of work, to get the same amount of utility out of the circuit. And again, it's just kind of fun to geek out on the data. Anyway, I've got thousands of more.
So when you say that, Brad,
yeah.
it does